All right, today we're going to demystify one of the most important ideas in all of math, set theory. And you know what's wild? It all kicks off with a concept you already use every single day, probably without even thinking about it. So let's just dive right in.
So let me ask you a question. Think about the days of the week, or maybe all the students in your history class, or even just the different fruits you've got sitting in a bowl in your kitchen. What on earth do those three things have in common?
Well, the answer is, they're all sets. And this one simple idea, just a collection of things, is, and I'm not exaggerating, one of the foundational building blocks for pretty much everything in modern math, logic, and even all of computer science.
Okay, so what is a set, really? Let's start with a super clean definition and the two simple rules that basically govern everything about them. A set is just a collection of well-defined objects. That's it. That's the official definition. And the objects inside the set, we just call those elements. So for our set of fruits, the elements might be apple, banana, and orange. Simple stuff. And here's the best part. To really get sets, you only need to know two. Let's call them golden rules. If you can remember these two things, you've pretty much mastered the core concept. And here they are. Rule number one, the order of the elements just doesn't matter. The set with 1, 2, and 3 is the exact same set as the one with 3, 1, and 2. The arrangement is irrelevant, it's all about what's inside. And rule number two, duplicates get ignored. So if you see a set with the letters A, B, B, and C, the set itself just sees A, B, and C. It only cares about which unique elements are in the collection.
Okay, so now that we know what a set is, let's learn how to talk about them. It's kind of like learning a new language, but one with only like 2 words. It's super easy.
Let's pretend we have a set, we'll call it set A, and it's got all the weekdays in it. Monday, Tuesday, you get the idea. How would we write, in math shorthand, that Wednesday is one of the things inside our set A?
We use this little symbol. It kind of looks like a curvy letter E. This notation right here is just a fast way to say Wednesday is an element of set A. That's all it means. Pretty neat, huh?
So, naturally, what about the opposite? How do we say that Saturday is definitely not in our weekday set?
You probably guessed it. You just take that same symbol and put a line right through it. This means is not an element of. So this little bit of notation is the math way of saying Saturday is not an element of set A. It's super clear and way faster to write.
All right, we've got the language down. Now we can start doing stuff with sets, like measuring them. And this idea has its own special name, cardinality.
Don't let the fancy word fool you. Cardinality is just the number of unique things inside a set. We write it by putting these 2 vertical bars around the set's name. You'd read this as the cardinality of A.
And most of the time, it's just as easy as it sounds. If our set A has an apple, an orange, and a pear, well, it has 3 elements, so its cardinality is 3. See? Easy.
But, of course, it can get a little tricky. Take a look at this set, set B. It's got the number 1, then it has a set containing 2, 3, and 4, then another set with 5 and 6, and then finally the number 7. See what's happening? We have sets being used as elements inside another set.
So here's a little pop quiz for you. Looking at this weird structure, what do you think the cardinality of set B is? How many actual elements does it have? Go on, take a second and count them up.
The answer is 4. I know, right? That might seem a little weird at first, but it's because we only count the top-level items. We have the number 1, that's 1. The entire set, 2, 3, 4, is treated as one single thing, so that's element number 2. The set, 5, 6, is also just one thing. That's number 3. And the number 7 is our 4th and final element. That's how we get to 4.
You know, that last example is actually the perfect segue into our next topic, the whole idea of sets living inside other sets.
We call this a subset. We say that set A is a subset of set B if every single element in A can also be found somewhere in set B. The symbol for it is kind of like a C with a line under it, which helps you remember that A is contained in B.
Let's look at a super clear example. Say set B has the numbers 5, 9, 1, and 3, and set A just has 3 and 9. Well, since every element in A, both the 3 and the 9, is also hanging out in set B, we can say for sure that A is a subset of B.
Now here's a slightly weird, mind-bending rule that you just kind of have to remember. The empty set, that's a set with absolutely nothing in it, is considered a subset of every single set that exists, including itself.
It's just one of those fundamental truths of set theory.
Okay, this all leads us to our final and, honestly, most powerful concept. If we can have subsets, what if we made a giant new set that contained all the possible subsets of another set? Well, that's a thing, and it's called the power set.
Let's actually build one right now. Let's say our set A just has two little elements, x and y. To build its power set, we start by listing the subset with 0 elements. Remember, that's the empty set. Then, we list all the subsets that have just one element, so x and y. And finally, we list the subsets with 2 elements, which is just the original set itself, x, y. And there you have it. That collection of all those other sets, that is the power set.
But you can imagine, what if your set had 10 elements? Or 50? Listing out every single subset would be a nightmare. But you don't have to. There is this beautiful, amazing formula for it. The size of the power set is always 2 raised to the power of the size of the original set. So in our last example, A had 2 elements, and its power set had 2 squared, which is 4 elements. It's like magic, and it works every time.
And that really brings us to the final big idea. We've seen that a set is just a simple collection with 2 really simple rules. But from that humble beginning, you can build literally everything from the logic that powers your phone to the deepest, most complex theories in mathematics. So the question I want to leave you with is this: how can an idea so simple be so unbelievably powerful?